of Mathematics at National Teachers College, Kabale. So in this video we are going to discuss projectiles. The next slide should show us the outline which we shall follow in our discussion. So we shall begin with a definition, example, then we discuss equations of motion or projectiles, and then last we give a summary. So what is a projectile? A projectile, as you can observe in the diagrams in this slide, this is a ball, a shell from a cannon gun, a stone, so like an object thrown. So a projectile is an object that was thrown by some force, continues in motion by its own inertia. You can see the examples. There are other examples, but we have not put them on this slide, like e.g. a mango falling from a mango tree. So we are going to discuss the motion of the projectile. And we shall consider a projectile which is projected at an angle theta with an initial speed u, that's to the horizontal. So if we are to begin with first of all knowing what do we need, we shall look at the motion of this projectile in two directions, the vertical and the horizontal. The horizontal, so we shall assume that the horizontal component, the initial horizontal component of velocity is u cos theta. If we resolve vertically, the initial component of velocity vertically or speed is u sin theta. Now if we take x and y to be our horizontal and vertical directions respectively, and then we take vx and vy as our horizontal and vertical, speeds after time t, then we move on. Now, however, we need to ask ourselves, why is it that when objects are projected upwards, they come back? Now there we put in the concept of gravity. So, because of acceleration due to gravity, the vertical motion of this object will be affected by gravity. So it will change with time. And in that case, we shall look at the velocity of this object changing with time. So it's affected by gravity. However, for horizontal motion, the velocity will not change because there are no forces acting on the particle horizontally. So if we take ax and ay, these two, ax and ay, has the definitions as our accelerations for the particle. This is the horizontal component ax, the vertical component. The vertical component is the opposite of gravity, because we are assuming that if a particle is projected upwards, it has to oppose gravity. Now, from the definition of acceleration, we know that acceleration is the rate of change of velocity, or it is the derivative of velocity with respect to time, implying velocity should be the integral of acceleration. So if we integrate equation 1, which is for acceleration, you should be able to get velocity. You can observe this is what we get. Now to remove these integration constants, this in green and this in brown, we use initial conditions at time equals to 0. What was the initial component of velocity horizontally? It was u cos theta. What was that of velocity vertically? It was u sin theta. So when we plug them into these expressions, we get equation 2 has our equations for velocity after time t for a particle projected at an angle theta above the horizontal. So similarly, if we integrate velocity, we should be able to get velocity of this particle after time t. So when you integrate to this component vx, you get the horizontal displacement. When you integrate this is a constant, so you get u cos theta t. When you integrate the vertical component of velocity, you get y. Then this one gives us negative half gt square plus u sine theta t, plus the integration constants which I have not indicated, because at time equals to 0, the displacement is 0, the horizontal displacement is 0, and vertical displacement is 0. So when you put them here, the integration constants become 0. As you observe horizontally, we have u equals to, so we have x equals to u cos theta times t, implying distance is equal to speed times time. So for horizontal motion, we shall always use this formula, which is distance displacement equal to speed times time, because for there is no acceleration horizontally. Now vertically, we shall use this equation, this and this one. These three for vertical motion are similar to Newton's equation of motion, where instead of acceleration we have negative g, and instead of u we have u sine theta, which is the initial component of velocity. So the other general results or general equations for a projectile. That's if we look at this. For example, if we look at this particle, which is if projected upwards, it will move in such a curve. So such a particle, it has here a limit, can't move higher than this height. So implying we have to discuss this. What time would it take to reach here? Or what would be the maximum height in such a case? And that's what we call the time at maximum height, and so on. So to solve this, we shall use equations for vertical motion. To begin with the first case for time at maximum height, if we use equation 2 for velocity after a time t, and then we know that vertically, when the object reaches maximum, it is momentarily at rest. So implying at maximum height, the object is not moving. It has a velocity of 0. So it gives us this. We plug 0 in the second equation of motion for velocity, like we are seeing in this red equation, this one. Plug 0, and when we simplify it, we solve for t, we get equation 4, which is t equals to u sine theta over g. This is the time for a projectile takes to reach maximum height. Now, what is that height? So we can use the equation for vertical displacement. That's equation 3. So if we substitute time at maximum height in this equation for vertical displacement and simplify, we get our maximum height has u squared sine squared theta over 2g. Yeah, in case there are any steps which are confusing, I think we can discuss later. Now, there's other equations like time of flight. How much time does a particle take while it is in motion? That's what we call time of flight. So if we use the equation for vertical displacement, which was y equals to negative a half, here it was y equals negative a half gt square plus u sine theta t. Now for vertical displacement, we are showing that when an object is projected up and then it comes back to the ground, vertically, when it is on the ground, its height will be 0. So initially at the point of projection, its height was 0, and when it falls back on the ground, its height will again, its displacement will be 0. So if we substitute the expression for displacement, that's equation 3, Where the displacement we put there 0, because after its flight it goes back at a displacement of 0. We end and simplify and solve for t. Our t is now the time of flight, this capital T. We simplify this expression. These are the steps. I think you can follow if you take time. You end up with t equals 2u sine theta over g. This is now the time an object takes in air. If it is projected from the ground and then it lands back to the ground again. The symbols, they hold the same meaning, it doesn't change. Then the horizontal displacement such an object would get would be obtained using equation 3 for horizontal displacement, where we had x equals to t times speed. Speed is now u cos theta. So this is what we have. So our range, now the horizontal displacement, the particle would take from the point of projection to where it lands back again to the ground, is what we call range. So if we use it, our range is called time of flight times speed. When we simplify, that r as u squared sine 2 theta over g. So this is an expression for range. However, if you want your object to reach as far as possible from the point of projection, maybe you want to hit a target which is very far from where you are and you are playing golf. So it is better you project such an object at an angle of 45 degrees. How do we get 45 degrees? We assume that here sine 2 theta can be maximum when it is 1. And if sine 2 theta is equal to 1, and you get the arc sine of both sides of this expression, then 2 theta is equal to 90 degrees. So if 2 theta is 90 degrees, it means theta is half of 90 degrees, which is 45 degrees. So in such a case, range would be provided by u squared over g, which we refer to in our expression here as maximum range, and particle can reach, or the maximum horizontal displacement a particle can reach from the point of projection. Now we have another general equation which we call equation of a trajectory. The proof, you'll try it during your free time. So the equation of trajectory describes the path a projectile takes during its motion. Like in this slide, it can be of this form or of this form. In this diagram, we are trying to indicate that for a projectile to pass a given point, there are two possible angles of projection it can be projected. Here, in our case, the first one would be when a particle is moving upwards to pass through such a point, or when a particle is coming back from the maximum height and passes through that same point. Another case with this equation, we realize that for a given value of vertical displacement y, there are two possible horizontal displacement we can get. For example, if an object to reach at certain height, to reach at such a height 2 times, one when it is moving up, another case when it is moving down. So the equation of trajectory is quadratic, as you can see. In horizontal displacement, which is x squared, you can see this, and also in the angle of projection, as you can see this equation, it is quadratic, so we can have two possible values of tan theta. So we try out some examples. A particle is projected from a point on level ground such that its initial velocity is 56 meters per second at an angle of 30 degrees above the horizontal. Take G has 9.8 meters per second squared. Find the time taken for a particle to reach its maximum height. So here we can either substitute, we can either use the equations of motion we had above, or we use the general expressions we obtained. And we still remember that at maximum height for vertical motion, the particle is at rest. That's at maximum height vertically. We assume it becomes at rest first before it begins coming back downwards. So if we use the expression for equation 2, and where there is velocity we substitute there 0, then we will solve for t, because g is 9.8 is given, u is 56 is given, theta is 30 degrees is given. So when we substitute them in such an expression and simplify, we get our time as 2.86 seconds. Alternatively, someone could have used the expression we got above for a particle for time taken by a particle to reach maximum height. Now, example 2, it's saying a bullet fired from a gun has maximum horizontal range of 2,000 meters. Find the muzzle velocity of the gun, i.e. the speed with which the bullet leaves the gun. Now, we have already derived the expression for maximum range, which was R equals to U squared over G. So we can use it, and where there is R, maximum range, we substitute here 2000. Then G, I took G as 9.8. And we already, this is given, so if we use R is equal to U squared over G, that's what we get. Here, this diagram is showing us the expression that the angles for a maximum range or horizontal displacement, the angle has to be 45. It's a reminder. Now, these are trial questions which you can discuss. You can discuss them via Facebook platform or WhatsApp platform. Number 1, saying a particle is projected from a point on level ground such that its initial velocity is 28 meters per second at an angle of 45 degrees above the horizontal. Take G as 9.8 meters per second squared. Find the time taken for the particle to reach its maximum height. Number 2, it's saying a particle is projected from a point on a horizontal plane and has an initial velocity u at an angle of theta above the plane. Show by using equation, that's the third equation of motion, v square is equal to u square sine square theta minus 2gy, that the greatest height reached by the particle above the plane is given by that expression. As you can recall, for us we used different expressions. So now here I want you to try this other equation of motion to get the maximum height. So you can still discuss that in your free time. Number 3 is reading that a particle is projected from a point on horizontal plane with an initial velocity of 140 meters per second at an angle of elevation 30 degrees. Find the greatest height reached by the particle above the plane. That's our number 3. I hope you discuss those questions. Now, for more revision questions, you can click on this, take this link, the revision questions. For notes, take this link. And for this video, if you lose it, you can still access it via this link on our Padlet. It is my Padlet. And other material I will be posting there, any comments or what. You can also still use my link for any observations concerning this lesson. Where you haven't understood, you can post on this link and inform me, or use our WhatsApp and Facebook accounts. So, in summary, we have discussed what a projectile is. Should be knowing the definition of a projectile. Then you should know the equation of motion to use for horizontal motion, where we said the x is equal to u cos theta times t. This distance is called speed times t. Horizontal motion doesn't depend on gravity, or horizontally the horizontal speed is constant. We have to take note of that. Then for vertical motion, we use equations similar to Newton's equations of motion, as you can see below. So these are the general expressions we have obtained. For maximum height, we have that h maximum is equal to u sine squared theta over 2g. Time at maximum height is this, u sine theta over g. Time of flight is, you know that the time of flight is times 2 the time at maximum height. Range, we have u squared sine theta over g. Then lastly, our expression, the equation of trajectory, which you must prove, which I've left for you, can discuss and consult where necessary. Thank you for your attention. My Gmail account consists in the slides, zabatmujungu@gmail.com. These are my contacts. You can call me, I'm always available. I'm reminding you that the class has a Facebook account with names NTC Kabare Mathematics Year 2, and a WhatsApp class NTC Kabare MTC2 2019-2020. So these are the names of our accounts for Facebook and WhatsApp. Thank you. Have a nice time. Now, for assessment,